name is Brandon Harris, and I work at a company called Electric Imp that helps manufacturers build connected Wi-Fi devices.
Well, you know, connecting Wi-Fi devices or connecting any devices really starts with communication protocols. Can you maybe just give us an overview of what they are?
Yeah, so when you think about a communication protocol, it's often helpful to sort of break it down and to first think about the physical layer. The most common one we use today is 2.4 gigahertz. That's the actual frequency in which it communicates. These are things like Wi-Fi and Bluetooth.
Mm-hmm.
You then have lots of, and the reason those are popular is that they're free to use worldwide. You'll often also see, cellular uses different bands. That's why you get so many different bands on your phone, and why a phone might work in one country but on another.
Mm-hmm.
And then you have some other different frequency spectrums that are often free to use, such as the 433 or 868 and 900 all have portions of the spectrum that are usable. And so, having a frequency is sort of the first start.
Okay.
Really what that allows you to do is to transmit a 1 or a 0, right? And you can encode that in lots of different ways. The next step up is really to agree on how those 1s and 0s are going to be transmitted and how you move data back and forth across that physical layer. And that's really where you start getting into the protocols. So Bluetooth
Mm-hmm.
is really much more about a protocol, a description of how you exchange data between one device and another, than it is about the actual underlying technology. In some cases, the protocol layer can run on multiple different physical layers. So it's really helpful to distinguish, that you're not just talking about a frequency, you're talking about how you're moving data on that frequency. And once you've sort of selected one of those, whether it's a standard that's Wi-Fi or Bluetooth or Zigbee or something else, or doing a proprietary low power, there are a lot of devices that, a lot of garage door openers, it's a undocumented protocol and things like that. So, they've invented their own mechanism for sending that information. And once you have that, you can start to think about, okay, what are the things I need, and how do I select the right protocol for me?
Well, something that comes to mind is you were saying, which is interesting, start at the frequency. So when looking at the frequencies, why would you choose one over another, or what are the common, I guess, frequency usages?
Yeah, so the big difference is a lot of it has to do with bandwidth in terms of the number of bits per second you can send. So generally, the higher the frequency, the more bits per second you can send.
Okay.
It also depends on how much of the frequency you're using. So there's a lot of other really technical aspects of that. Generally, for highly complex, really intelligent, data-intensive devices, you want to be up in a higher frequency range. That's usually where 2.4 is a gigahertz is a sweet spot. That's why we see Bluetooth and Wi-Fi really being at home there. Cellular actually uses some lower frequencies, largely because it's a very old standard. When you think about the earliest cell phones, and they're still using the same frequencies. Back when it was a portable briefcase, right? They're still using the exact same physical layer or spectrum that they were back then. They've just gotten more efficient at packing 1s and 0s into that same available space.
Right.
And then a lot of the unlicensed bands that are lower frequency are good for sending small amounts of data. A garage door code, it only has to send a couple bits to sort of uniquely identify itself and provide a little bit of security. And sort of the flip side of that is, of course, cost. At lower frequencies, you can build very low-cost transmitters and receivers. They can be built out of discrete parts. It's very, very cost-effective to build those devices. As you go to higher frequencies, more modulation is required. There's more devices already in that space, and so that really helps to define what you're looking for is how much data you want to move and what your cost target is.
How much data, what your cost target is, and does environment have anything to do with this? Range or anything like that?
Yeah, so range also comes into play. There are a lot of things even within the protocol that you can do to affect range. Bluetooth and Wi-Fi run in the same physical space, but at very different ranges. Wi-Fi is, we've seen ranges, well, in extreme cases, a mile or more.
Really?
that generally requires dedicated sort of directional antennas. But in a home environment, you're talking about hundreds of feet, whereas Bluetooth is typically capping out around 50 feet to be usable. So the main thing is understand, and as you go to lower frequencies, that range often increases, and the types of walls and sort of environments. In an open space environment, a lot of it's dictated by just your output power. So you can have different levels of transmit power that affect your range, or you can do it by changing the frequency.
Okay, so I can understand then the frequency is important, in the different scenarios. So why is the protocol important? Because the frequency, like you said, it gives you the ones and zeros, but who cares about the protocols?
So the protocol is actually almost certainly more important than the frequency, because it really defines how you're going to use your available bandwidth and things like that. So Bluetooth and Wi-Fi are designed for very different applications. Bluetooth is really designed to do very short range, most of the time less than 1 meter, right, from your wrist to your pocket, and be very person-centric. And so they've made the design decision to optimize for power rather than range.
The protocol.
Right, at the protocol layer. And how they're using the available spectrum and things like that. And they use smaller slices of the spectrum because they need to push fewer bits through, and that allows them to get to be more power efficient. So a lot of it comes back to power. In some cases, it also depends on how many devices you want to support concurrently. There's a physical limit to the number of bits that can be packed into the air around us.
Is there?
There.
I guess there is.
Right. I mean, at the end of the day, there must be.
Yeah.
It may be orders of magnitude more than what we're capable of receiving right now.
Right.
But as you go up in those levels of interference, the complexity of those things grows.
Yeah.
And so the protocol really defines how your devices are going to interact, and really it requires a very deep understanding of what you're trying to achieve and what your customers' needs are, what the goals of the project are, in order to establish what protocol is the best for you.
Yeah, no, that makes sense. So the radio frequency, there's obviously constraints there, and for your particular use case, but then the protocol is very much use case oriented in the sense of what you're trying to achieve with it. And if you were to just use generalities in terms of, consumer IoT, enterprise IoT, industrial IoT, infrastructure IoT, what are we seeing for these protocols and frequencies?
So we see a lot of things in 2.4 gigahertz.
Yeah, it seems like all the new kids, all the popular kids are there.
It's a very popular band, and it's being, part of that is the cost has been driven.
And this is across all the different markets?
Across all the different markets. It's relatively low in interference. One of the other big things is the frequency also generally defines the size of your antenna. And
important.
The size of your device.
Important,
so
yeah.
As we go to smaller and smaller devices, smaller antennas are easier to fit into those devices.
And smaller antennas are for higher frequency?
Are for higher frequencies, so they're inversely correlated.
Yeah.
So when you think about an FM radio that has a great big whip antenna in your car, that's because it's running at 100 megahertz.
Right, and there's a big old wave going.
It's a big long wave, and it's great at traveling long distances. As you go to higher frequencies, that wavelength gets shorter and shorter, and so there are 2.4 gigahertz antennas that sort of wrap in on themselves that are, I think we've seen ones that are less than 2 millimeters long. We're talking about putting a tiny little part on your board. The performance isn't great, but
But again, it depends.
It's completely reasonable.
Depends on the protocol, maybe.
It depends on the protocol, and for things like Bluetooth, that's perfectly acceptable, where they're designed for low range.
Okay, so what you're saying is the frequency that seems to be popular is the 2.4 gigahertz, and then the protocols, is it kind of across the board, or can you kind of generalize?
So protocols, we're kind of right at the edge of adoption of a lot of these things. When you actually look at the difference between what people are talking about and what has actually been deployed, they're fairly different.
And what do you mean?
You know, we have this idea that we're going to have the second coming of the smart home, and that people are automating their houses today, and they're having these rich, wonderful experiences, and that there are smart light bulbs. And the reality is, smart light bulbs are on the market today. Nobody has really created a compelling enough solution for mass market adoption. You know, it's mostly still fringe adoption and early adopters who want to try the technology, not because they have a driving need for it. I think that's changing, and I think it's about to start changing pretty quickly. And we're going to see more devices that are driven by real customer desire rather than what we can do with the current technology. And that will start to define what those devices are, really starts to define the protocol. I'm, you know, obviously a strong believer in Wi-Fi. I think it's great to leverage existing infrastructure.
Sure.
You know, what $50 buys you today in terms of a Wi-Fi router is tremendous. And it's really hard to beat those economies of scale. And they fall every year. You know, we found a $12 Wi-Fi router, right? It's like, how do you know, how can any other hub or anything else compete with that kind of low price? It's incredibly compelling. So I really like Wi-Fi as a protocol for those things. I think also Bluetooth, because of smartphone adoption and the number of wearables and things like that, is really driving adoption. It's going to have a really hard time in industrial and enterprise because it's really phone and person based and not sort of infrastructure based, and those tend to be biased more towards that.
Whereas Wi-Fi could be adopted.
Whereas Wi-Fi,
as long as you have the power, right? I mean, because there are some limitations. Obviously,
power is a something we talk about all the time. We refer to the power story. And it's one of the most frustrating things as an engineer. We have tremendous technology, and we can do so many things and access to so many great sensors, and then
gotta light them up.
You know,
changing the batteries.
Changing the batteries, and I just have a hard time believing that that's where the future is going. That it's going to require me to go around and change batteries every so often and things like that. So it is possible to do battery powered devices, and understanding, again, this goes back to understanding your really core functional needs. You know, it may be that you really need that real-time data, and it has to be, in which case it pretty much has to be wall powered, because that's the reality we live in today. Is we don't have something that can create this always available, always on, and ultra low power, except in very odd use cases. Something's going to have to be plugged in somewhere.
Something's got to be plugged in somewhere.
Because all of those things they all require power.
Damn power.
Yeah.
All right, well, thank you very much. I enjoyed the interview.
Thank you very much for having me.